Okay, in this video we'll be looking a little bit more deeply at the idea of thermal energy and specifically the transfer of thermal energy from one object to another. And an important concept in examining thermal energy is the idea of the specific heat capacity. So the specific heat capacity is the energy required to raise the temperature of a unit mass, that is to say 1 kilogram, of a substance by 1 degree Kelvin or 1 degree Celsius. The Kelvin scale, just to remind you, is based on the Celsius scale. So changing the temperature by 1 degree Kelvin is the same thing as changing it by 1 degree Celsius. Real important in this word, specific heat capacity, the word specific specifically refers to the idea of unit mass. And we'll see that come up again in other contexts later in this topic, and then also even in other topics with reference to energy. And the word specific refers to a unit mass. That means to say per kilogram. So since it is defined as the energy to raise the temperature by 1 degree Kelvin or Celsius, we can write an equation for C. And that equation would be the energy. So this is going to be the energy per unit mass per degree Kelvin. So this is going to be Q. The energy per kilogram per degree Celsius or per Kelvin, where Q is thermal energy. So we use the letter Q when we deal with thermal energy as just a way of differentiating it from other forms of energy. Obviously, M is the mass, and delta T is the change in temperature. More often than not, we will use this equation in this form. We'll solve it for Q. And this will allow me to calculate the amount of thermal energy either absorbed or released by an object who has changed its temperature. It could be that the object has increased in temperature, in which it would have gained this energy Q, or it could have reduced its temperature, and in that case it would have lost that amount of energy Q. Very important that the units for this are joules per kilogram per Kelvin, or it could also be per degree Celsius. It would be very common to see degrees Celsius here also. So the units tell you what it is, the amount of energy to raise 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius. So just to give you some examples of what would be like common specific heat capacities for different substances, let me give you 3 examples. So the 3 examples are for iron, which has a relatively low specific heat capacity. Typically most metals have relatively low specific heat capacities, maybe as low as in the 200s up into the low 400s or 500s maybe. There are a few metals that get a little bit higher, like aluminum. Aluminum is around 900 joules per kilogram per Kelvin. Moving up then, away from the metals to a material, a common rock, and near the surface of the earth would be granite, or even within the earth. And it has a specific heat capacity of 790 joules per kilogram per Kelvin. So a little bit higher. It takes a little bit more energy to raise 1 kilogram of this substance by 1 Kelvin. And if you go to one of the highest ones that I'm personally aware of, would be water, which has a specific heat capacity of 4,186 joules per kilogram per Kelvin. It's very, very high specific heat capacity. And the difference between these specific heat capacities should kind of explain some of the things that you might see in the everyday world. So a good example would be when you travel to the beach. So when you travel to the beach, you're going to walk across sand, which is basically made of the same thing that granite is made from. Granite has large amounts of silica, which is exactly what the sand is made of, and also where the sand ultimately originates from. So the specific heat capacity of sand is pretty close to 800 joules per kilogram per Kelvin. Whereas when you go swim in the water obviously is closer to 4,200 joules per kilogram per Kelvin. So when you walk across the sand after the sun has been out for quite a while during the course of the day, the sand is very hot and might even burn your feet. Whereas when you get in the water still feels fairly cool. And that's explained by the difference between their specific heat capacities. So let's say that we give 1 kilogram of water and 1 kilogram of granite the same amount of energy. Let's give them, for example, let's say around 4,200 joules. So if I give a sample of water, 1 kilogram of water, 4,200 joules, it's only going to raise its temperature by 1 degree Kelvin. But if I give that same 4,200 joules to granite, its temperature is going to rise by more than 5 degrees. So substances, the way that they change their temperature differs greatly dependent on what we refer to as their specific heat capacity. So this is why during the course of the day, as the sand and the water absorb the same amount of energy, the sand heats up much more in terms of its temperature, that is to say its temperature will change much more than the water does. Now obviously I'm giving you two solids and this is a liquid, but of course any substance can have a specific heat capacity, and it will typically have a different specific heat capacity depending on whether it's in the solid, the liquid, or the gas state. So there is also ice, for example, and ice has a specific heat capacity of about 2,200 joules per kilogram per Kelvin. Or we could look at the other side of water, and that is steam. Steam, coincidentally, has a very similar specific heat capacity to ice. Its specific heat capacity is about 2,010 joules per kilogram per Kelvin. Obviously, water turns into steam at 100 degrees Celsius, but of course you can then heat the steam up even hotter and hotter and hotter. You can make the steam as hot as you want. Similarly, the ice will start to form in water when you get to 0 degrees C, but you can go lower than 0 degrees C. You could go down to minus 10 or minus 20. You can go as low as you would like to, down to absolute 0. So these give you some sense of what the specific heat capacity is and how it varies from one substance to another. So let's take a look at a few example problems to just see how this concept of specific heat capacity can be used in actually solving problems or understanding what's happening to a substance as it absorbs thermal energy. So we'll look at this problem, and let's assume that you have a water heater at your house, and it would be common for a water heater to maybe hold 300 liters of water. And what we're going to do is we're going to turn the water heater on, and when we turn the water heater on, it's going to take the water from 20 degrees, which is very close to room temperature, up to 55 degrees, which would be typically a temperature that you might use for taking showers or for the hot water in your house. So in this case, this is a very straightforward calculation. We're simply going to use the formula Q equals MC delta T to calculate the Q for this particular example. So Q is equal to MC delta T. Now, one thing that's really important to understand, or to remember, I should say, is that 1 liter of water is equal to 1 kilogram. This is part of how the metric system was defined. So there is a connection that you have to memorize. This is required on the IB exam, that you understand that 1 liter of water is equal to 1 kilogram of water. It is the mass of 1 kilogram of water would occupy 1 liter of volume. So in this case, where it says 300 liters, I could just as easily say 300 kilograms. So 300 liters of water will have a mass of 300 kilograms. We've already seen that the specific heat capacity is 4186, or you can use 4200 as an approximation for C. And then in this case, we want to change the temperature from 20 to 55. That would be 35 degrees Celsius, which is the same thing as 35 kelvins. So in this case, the Q then comes out to be 300 times 4186 times 35. So we're going to round this. I'm going to give you two ways of writing the answer. We only had two significant figures here, so that means that we can only keep 2 in the final answer. So I am going to cut that answer down to 4.4 times 10 to the 7th joules, or alternatively, we might say 44 megajoules. So that's pretty straightforward. That's just a simple calculate the amount of energy that's absorbed, or this could be released by water. If the water was taken from 55 down to 20, then we would have released that amount of energy. A water heater typically is going to be powered. It may either be electric or it may be gas powered. So let's just extend the problem a little further to previous topics that we talked about. Important aspect of your water heater will be the power, which is how fast can it pump the energy into the system. So for that, I'm going to just pull this up just a little bit further, and we're going to extend a problem to assume that the power rating for the water heater is 20 kilowatts or 20,000 watts. Then the question would be, how long is it going to take this water heater to raise the temperature from 20 to 55 degrees? So in this case, we're using the equation that P is equal to W over T, but we can modify the equation because, just to remind you, work, energy is the ability to do work, and that includes thermal energy. So I could just as easily say Q over T. So this is a slightly same equation, still energy over time, but in this case we're talking about thermal energy. So this will lead to the equation that T is equal to Q over P. So using the numbers from the previous calculation, that's going to be 44 megajoules divided by 20 times 10 to the 3. So I'm just going to keep the number that was in there, divided by 20,000, and that gives me 2197.65. So taking that down to the correct number of significant figures, again, I only had 2 significant figures with this previous number, so T is going to be equal to about 2,200 seconds, or I could divide by 60, and that number is 37 minutes. So a water heater with a power rating of 20 kilowatts will be able to pump in 44 megajoules worth of thermal energy into the water in 37 minutes. So this is like a common, it's a very simple problem, but this is basically a level 1 problem. So we really want to extend this to a little more challenging problems. And the more challenging problems will be typically when you have 2 substances, maybe they have the same specific heat capacity, maybe they have a different specific heat capacity, but 2 substances, or maybe even more, in which you combine them together. And what you should know at this point will happen when you take 2 substances at different temperatures, they will exchange thermal energy, they'll exchange Qs, until eventually they achieve the same temperature. And so we want to look at how do you address a problem in which you are going to allow this exchange to occur, and what we usually want to know is what will be the final temperature of this mixture of stuff that we're going to put together. So let me move this out of the way. And let's revisit this idea of thermal equilibrium. So the idea of thermal equilibrium is that the 2 substances will exchange the same energy, so therefore they no longer are changing temperature. If something is hotter, then it will predominantly, the net direction or the net flow of energy will be from the hotter object to the cooler object. And so the 2 will exchange energy until they reach the same temperature. They will still continue to exchange energy, but they exchange the same amount of energy. So therefore they no longer continue to change. So just using really an extension of the idea of conservation of energy in a closed, meaning no mass is allowed to come in, and isolating, meaning no energy or no forces are acting from the outside, the total energy in a system must remain constant, because otherwise that would violate conservation of energy. So this first sentence, in a closed and isolated system, the total energy must remain constant. That would look something like this. If I added Q1 for substance 1 to Q2 to Q3 plus whatever other number of objects are in this system, then that would have to be equal to a constant. Okay, so that's one way of thinking about things. But the way we're going to look at it is we're going to look at it more in terms of the exchange of energy. So let's say we have 2 people and each person has $20. So the total amount of money that they have would be $40. That would be my constant. Now they can exchange money with each other. Let's say one of the people gives $5 to the other person. So now one person has $25, the other person now has $15, but the total, it still adds up to $20 because they haven't exchanged anything with the surroundings. The system is closed and isolated. So that's one way of looking at it, is to look at the total amount of energy that is in this system. but we can also look at it in terms of the energy that is exchanged. And what would have to be true in a system that's closed and isolated, where the total amount of energy remains constant, is that the energy that's exchanged must be equal. So if I can go back to that example I just used a second ago, when I say that one person gives $5 to the other, that means that one person has lost $5 and the other person has gained $5. So those two energies that are exchanged, they have to be equal. And if I added those two together, they would have to add up to 0. So one guy got a positive 5, the other guy got negative 5, and 5 and negative 5 is 0. So as long as they don't exchange anything with the outside, now then that would actually cause the number to be different, then the energy that is exchanged must add up to 0. If I add up all the energies, who got positives and who had negative, that amount of energy must be 0. So that would look a little different. That equation would look like this. That would be that delta Q1 plus delta Q2 plus delta Q3 must be equal to 0. If I add up all of the energies which have been exchanged, they must all add up to 0. Because if they don't, then that means that energy has somehow left the system. Either energy has gone out of the system or energy has come into the system. So people can exchange. Q1, Q2, and Q3, they can exchange. They can give energy back and forth from one to the other. But the total amount of change of energy has to be 0, otherwise there'll be missing energy. Or in my previous example, there would be missing money. So let's simplify this down. Let's go back down to where we only have 2 objects. So let's try something a little bit more concrete. All right, delta Q2 equals 0. So we'll just look at a little bit simpler example. So this is one way that we can look at the problem, and I'm going to show you how to solve problems using this concept of the idea that the changes in energy, the energy exchange, must add up to 0. But in some cases, we might do something a little bit different. What we might do is just acknowledge that if I only have 2 objects, and the 2 objects are going to exchange the same amount of energy, then I could say this, that delta Q1 must be equal to the opposite of delta Q2. Now, we can even go a step further, so just realize that each of these Q's involves a delta T. So there is some change in the temperature. One of them will be a positive change in temperature, one of them will be a negative change in temperature. So one thing that we may end up doing is simplifying this even further to just simply say that delta Q1 must be equal to delta Q2, just recognizing that somebody must have gained and somebody must be losing energy. And so what we have to do in order to do this, it's a little bit tricky, because what could happen is you end up with a statement that doesn't make any sense. You end up with a positive number being equal to a negative number. So normally we would do the change in temperature, delta T, as TF minus TI, the initial temperature. Okay? But just realize one of these guys is going to produce a negative delta T, because their temperature is going to be cooler when they finished than when they started. So you have a hot substance and a cool substance, you bring them together, and then their temperatures slowly come until they meet somewhere in the middle. So the change in temperature typically is TF minus TI, but in this case, if I use this simple way of looking at it, I would just simply subtract the big number, the little number, from the big number in order to produce a positive value for the change in temperature, just recognizing, not worrying about the negative aspect of it, but just the idea that one guy gained, and what the guy gained here, this guy on the other side must have lost. You know, if, for example, we had 2 substances, one at 20 and one at 55, and we brought those 2 together and they met at 35 degrees Celsius, then in this case, this would be 35 minus 20, right, which will give me positive 15. But technically, if I do final minus initial, that would be 35 minus 55, which would be negative 15. So ultimately, what would happen is, if I take this negative sign into the delta Q, what would happen is these 2 guys would reverse. So I would do the initial temperature, which is the bigger temperature, minus the final temperature, and in that case I would end up with a positive 15. So you can use either method. You can stick to the straight, add them up, and they must add up to 0, and just let the negatives will work themselves out, because the negative will be built into the delta T. Obviously it will not be built into the mass or into the specific heat capacity. Those numbers are both positive all the time. But the delta T could be either positive or negative. And in this case, if I have two substances, one of them will have to be positive, one of them have to be negative. Or I can just take a simpler approach and just realize that the delta Q's must be equal to each other, and I'll just subtract the temperatures in such a way that I get the positive value all the time. So let's take a look at how, like in practice, how will this actually look when you actually solve a problem. So let's bring up an example problem. And this is an example in which we're going to involve mixing two substances together. So what we'll do is we will take 150 milliliters of water that's at 20 degrees Celsius, and we will pour it into a container, a calorimeter, which has 250 milliliters of water at 95 degrees Celsius. And we want to know what will be the final temperature of the mixture. So I'm going to do this problem twice. The first time I do the problem, we'll ignore the calorimeter. Just to keep things simple, we'll ignore the calorimeter so that we can just focus on what will happen between the exchange of energy of the two waters. So again, we would do delta Q1 plus delta Q2 must add up to 0. So in that case, that means that M1, I'm going to say CW because that's water in both cases, times delta T1 plus M2, that's this guy, times the specific heat capacity of water, times his change in temperature. He has a different change in temperature. That must all be equal to 0. Okay, and all the numbers I have are right here. So the way that this would work is like this. Remember, a liter of water is a kilogram, so a milliliter of water would be the same thing as 1 gram. So this mass would be 0.150 times the specific heat capacity of water, 4186, times the change in temperature. But now realize I don't actually have both temperatures. I only have one of the temperatures. So what I don't know is the final temperature. I don't know what TF is, but I do know that the initial temperature was 20. Okay, I'm going to add that. That's the delta Q for the 150 milliliters of water. I'm going to add that to the delta Q for the 250 milliliters of water. So that's 0.250 kilograms times 4186, same specific heat capacity as the other guy. And now it's going to be TF minus 95. And that's all going to be equal to 0. Okay, so now we just take this to the calculator. Let's start calculating a few of these numbers, and then we'll start bringing the temperatures, the TFs together. So in this case, that would be 0.15 times 4186 times TF. So that is 627.9 TF minus, just need to multiply that by 20, minus 12,558. So that takes care of this entire calculation right there. Now we'll focus on the second one. Plus 0.25 times 4186. That is equal to 1046.5 TF. And then we'll just multiply that times 95 to get the second number, which is minus 99,417.5. That all equals 0. Now I'm just going to bring these two numbers together. Here's the two numbers with TF. Here's the two numbers without that. And so the second number, I'm going to add the 99,417 and the 12,558 to get a total of negative 11,975.5 equal to 0. And we'll add the 627.9 plus 1,046.5. And that is 1674.4 TF. Sorry, I didn't quite leave enough room there. And so the way I'll calculate the final temperature is I'm going to move this guy over to the other side, 11975.5. I will divide by 1674.4 to get the final temperature. And that is 66.875. And so we will list the final temperature as 67 degrees Celsius. Okay, so The final temperature is 67 degrees, and now we're going to just make a little slight modification. We're just going to bring the calorimeter into this problem. And in order to bring the calorimeter into the problem, there's just going to be a Q3. Okay, so the calculation is going to go very similar, except that there's going to be a delta Q1, a delta Q2, and this time there'll be a delta Q3, and that is to take into account the calorimeter, the effect of the calorimeter. So we're going to assume that this calorimeter is made from aluminum, which has a specific heat capacity of 900 joules per kilogram per Kelvin, and that this total mass of the calorimeter is 225 grams. So much of the calculation is exactly the same as it was in the previous part. So we have M1 CW delta T1 plus M2 CW delta T2 plus this new substance M3CA for aluminum times delta T3, delta T3. Now, it will turn out that the temperature change for delta T2 and delta T3 is actually the same. It is the same delta T, because of course they started with the same temperature of 95 degrees, and they're going to eventually come to the same temperature when all three of these substances finally arrive at the equilibrium temperature. It's going to be the same final temperature too. So those will actually be the same quantity. So we have the numbers from the previous problem. So I'm going to go ahead and bring some of those numbers down. For this one, that's going to be 0.150 times 4186 times, in this case, TF minus 20. Okay, now what I'm going to do is a little bit different, because I do know that these two are going to have the same temperature. I'm going to bring these M2CW and the M3CA, I'm going to bring them out. So I'm going to put a bracket. So this is going to be, the number from the top was 1046.5 plus the the M3CA, so that's going to be 0.225 times 900, that is 202.5 times the final temperature minus 95, that'll be equal to 0. So just pulling some of this stuff together. So on this side we ended up with 627.9 TF minus 12,558 plus, so now we're going to get the number for the TF, that is 1046.5 plus 202.5. So that's going to be 1249. 1249 TF minus that same number times 95, which is 118,655. And that's all equal to 0. So now, just like we did with the previous problem, we'll go ahead and add all this together, and then we'll solve for the final TF. Now, you could have handled these separately from each other. There's certainly nothing wrong with doing that. You can handle these as two separate calculations, to handle this one, and then just there'll be 3 TFs, I'll bring all those together. There'll be 3 other numbers, I'll bring all those together, and then we'll take care of the algebra from that point. So just bringing all these numbers together, I'm going to add this to the 12,558. So it is minus 131,213, that's equal to 0. And we had 627.9 plus 1249, and that is 1876.9 TF equal to 0. Apologize for that. So therefore my final temperature will be 131,213 divided by 1876.9. And that is going to be 69.909. So the final temperature we will call, based on the number of significant figures, that will be 70 degrees Celsius. And it should kind of make sense that this number is a little bit higher than the previous number. We had 67 in our previous calculation. Now we're getting 70, so about 3 degrees warmer, because some of the energy from the calorimeter is being shared with the cooler water. And so it makes sense that the temperature will be a little bit warmer because there's additional energy being taken into account through this calculation. So this basic principle of adding up all of the delta Q's and setting them equal to 0 should allow you to solve almost any problem that has to do with just energy changes or mixing of substances at different temperatures.